All right, let's do this. So today we're going to finish out our discussion of alcohols by talking about a specific class of reactions of alcohols which are called dehydration reactions. All right, we talked about hydration reactions. And in a hydration reaction, we are preparing an alcohol from what? An alkene, yes. All right, cool. All those preparation of alcohol reactions from alkenes where we add water to that alkene in order to create an alcohol. So then a dehydration reaction, we're going to take that alcohol and turn it into what? An alkene. All right, so we can carry out both of these reactions in the lab. All right, so let's just talk for a second about our equilibrium here between our alkene and our alcohol. All right, converting an alkene to an alcohol is favorable from the standpoint of the bonds that are broken and the new bonds that are formed. You get much more energy forming those new carbon-oxygen and carbon-hydrogen bonds than you have to put in to break that carbon-carbon pi bond. All right? So from a bond breaking and making standpoint, or a delta H standpoint, this is favorable. I'm just going to say bond making and breaking, all right? And to be clear, what I mean by that is, remember, you would have talked about how in any chemical reaction you would have to put energy in to break bonds, and then energy is released when those new bonds are formed. There's kind of this give and take, and a process is considered favorable if the energy that's released, the energy that's put out when those new bonds are formed, is greater than the amount that you have to put in to break the old bonds. Okay? So breaking that carbon-carbon pi bond to form our alcohol, to form those new carbon-oxygen and carbon-hydrogen bonds, that is a favorable standpoint from looking at those bonds. All right? But interestingly, the reverse process is favorable from that other very weird thermodynamic variable, right? Both of these are combined into that free energy, whether or not something happens, delta S. All right, these are favorable from an entropy standpoint, because when you break up this alkene, it's really because you're taking this big complicated structure and you're making it into these two smaller components. Right? That's always an entropically favorable thing, is to take something big and complicated and break it up into two separate things. Right? So that means one of these is going to be more preferable at high temperatures, and that is the entropy one, right? Entropy is sort of scales with temperature, so at high temperatures we can sort of prefer this one way or the other. Okay? So entropy favorable, let's just say, because we're breaking it up into smaller parts. Okay? So what we can say is that our dehydration reaction is favorable at high temperatures. The one is that delta S reason, because delta S scales with temperature. I mean, just to be clear, I'm talking about that delta G equals delta H minus T delta S business, right? That S is tied to that T variable temperature, so as you increase temperature, that term kind of dominates in that expression. Don't worry, we're not going to do any math with that, all right? But this is what I'm referring to, okay? There's also one very, very cool kind of practical reason why you can do this at high temperatures, and that is, let's just take a look at a very simple kind of alkene and alcohol combination. All right, which one of these is going to have the higher boiling point, my alkene or my alcohol? The alcohol, by like a butt-ton, right? Because the alcohol can form those very favorable hydrogen bonding interactions, right? Those very strong intermolecular interactions, and alkenes can't. They're completely nonpolar. They only have dispersion forces, right? So this is low T-boil, and this is a high T-boil, which means if I hook up this reaction to a distillation apparatus, as soon as that alkene product is formed, it's going to fly off into the gas phase away from my reaction mixture, and I can distill it out the other end, right? So there's this very sort of practical, when we set this up, Le Chatelier's principle we can take advantage of. As this low boiling point compound is going to be formed, I'm going to simply remove it from my reaction mixture, which will have the effect of pushing that equilibrium back in favor of that alkene. Right? So by removing it as soon as it gets formed from that reaction mixture, we help shift the equilibrium back in favor of that alkene, like continuously. So we can do it first of all, entropy is going to help us out there, but also we're going to do it in a distillation apparatus. Did y'all do this in lab? Did y'all dehydrate an alcohol? Oh, that's a bummer. It's a pretty cool one. The product smells really, really bad. That could be any reaction, I guess, in organic chemistry. All right, cool. So let's work on how we get our products here, all right? So we're going to start simple and then we'll complicate things. Let's take 1-butanol. Again, talking about dehydration. Okay. I'm going to tell you my product here is then 1-butene. And obviously, just by looking at this here, we can see that I have to lose that OH from my reactant side, right? I'm going to get rid of that oxygen and its hydrogen. But importantly, what else am I losing in this reaction from the reactant side to the product side? Not just O and H, but what else? Another hydrogen as well. Okay, so if we look, over here, this carbon has 2 hydrogens. And over here, that same carbon only has 1. Right? Again, the exact opposite of that hydration of an alcohol, where we put on one side the OH, and on the other side, we stuck a new hydrogen on there. Right? We're going to do the same thing. We got to remove the OH from one carbon and a hydrogen from its neighbor. All right, so this is going to be important. We're going to say we're going to remove an H from our neighboring carbon. All right, and we sort of said dehydration at this point, but practically how do we do a dehydration reaction? We use very concentrated acid, concentrated sulfuric acid. And again, you can shift this equilibrium in favor of that alkene by raising the temperature. Cool. All right. Let's do another one here. 3-methyl-2-butanol. We're going to hit this with our concentrated sulfuric acid and heat. And I'm going to tell you that there are two products here. Everybody take a minute and predict the two products of our dehydration reaction. All right, so I need to form a alkene from this alcohol here, right? I'm going to lose the OH group, so that means that this carbon is going to be a part of my new carbon-carbon double bond, all right? But then it's going to form that new carbon-carbon double bond with one of its neighbors. And in this case, it's got two distinct neighbors, which is why we can form two distinct products here. We would get one alkene if the hydrogen was lost from that orange carbon. All right, so now my new double bond is between orange and blue. And I would get a different product if that alkene carbon-carbon bond was formed between the blue carbon and the green carbon. All right, so like I said, we got two distinct alkenes that will form in this dehydration reaction, okay, depending on which one of those neighboring carbons loses their hydrogen. All right, now, I'm going to tell you, one of these two products is our major product. The other one would still be produced, but it would be considered the minor product. It's produced in a smaller amount. If we look carefully at these two structures, I'm going to get rid of my coloring here. Okay? Which one do we think is the major product of this reaction? The one on the left or the one on the right? On the right. And why is the one on the right? More substituted, more stable, right? Just a lower free energy. The equilibrium will favor the formation of that lower energy product. So absolutely, this one is just mono substituted. It's only got one carbon neighbor. Whereas this one over here is tri substituted. It's got three carbon-carbon neighbors. So absolutely, this is our major product because it's more stable. And really by more stable, in this case we mean more substituting. All right, cool. All right, we got this another alcohol here. I want everybody to take a second and see if they can't give me the dehydration products. And here I'm going to tell you that there's not one, not two, but 3 distinct products that we could get from this reaction. 3 distinct alkenes. All right, 2 of them should be pretty easy to get based on what we discussed previously, but then I want you to think carefully about how we would get that 3rd potential product. So I would get 1 alkene if that double bond forms between the blue carbon, which has that OH group, and its neighbor, the orange carbon. My second alkene product would be if my double bond forms between the blue carbon and the green carbon, its other neighbor. Let me try to make a little bit of room. All right, but I told you that there was a 3rd product. So what would my 3rd product be here? No, that's a very good guess, and we will talk about mechanism and shifts and all that jazz here in a bit. That is actually not the case here, all right? What we need to remember is that double bonds are frozen, but single bonds are not, which means that this alcohol right here, as it's traveling through space, this single bond is rotating around and around, right? Which means that every once in a while, the alcohol is not in that extended conformation, but rather has its carbon pointed down. And if we take this thing and dehydrate it, we wouldn't get our trans or our E product like we have drawn here. We would get our other stereoisomer of this same alkene, of this same 2-butene, the Z2-butene. All right, so because of stereochemistry, we now have this 3rd product, our other stereoisomer of 2-butene, the Z2-butene. All right, I guess just to be clear, this one was 1-butene because it was between that first carbon. This is 2-butene, but it is a specific stereoisomer of 2-butene, the E2-butene. So we also get the Z. All right, so again, let's think about major and minor products here. Based on what we discussed in the previous example, which one of these three is definitely going to be one of our minor products? The 1-butene, right? The less substituted. 1-butene is only mono, whereas 2-butene is di-substituted. So this is a minor product. But what about my E versus Z2-butene? One of these is going to be our major product of this reaction. The other one will be produced, but in a smaller amount. All right, what do we think is more stable, E2-butene or Z2-butene? Right, and that is just a simple sort of sterics. These two groups want to be as far apart as possible, right? Big groups don't like being next to each other. Sterics, right? So absolutely, our other minor product is going to be that Z conformation. So the E2-butene is our major product, okay? And again, we said that this one was our minor product because it was less stable due to sterics. The 1,2-butene we said was less stable because it was less substituted. Now we have this other complication of our stereochemistry, all right? Simply said, big groups don't want to be next to each other, right? They want to be as far apart as possible. Cool. All right. So let's do one more here. All right, so how many products do we get? Should have 3, okay? So, very simply, I'm just gonna copy and paste. I'm gonna draw a double bond to one neighbor. I'm gonna draw a double bond to the other neighbor. Boom. Okay? But again, we have to worry about whether or not we have those stereoisomers. So how am I supposed to know if there's gonna be additional products? Well, we gotta look and we gotta ask ourselves, does this double bond have any stereochemistry? If you were to name this thing, would you have to put E or Z in front of it? No, because that orange carbon is bound to 2 identical groups. Cool, done. That's the only one for that one. When I go on to this one, if I were to name this one, would I have to use E or Z stereochemistry in there? Yes. Okay, so for this one here then, that means that that's not the only product. I'm gonna have to also draw another one where I swap those 2 groups. All right, and I could either pick this one and this one, my propyl group and my methyl group, or I could pick my hydrogen and my methyl group just because it's easier for me to draw. I'm gonna move this one up. Boom. Okay, if you'd swapped the other 2, that would have been just fine. That would have been the identical molecule. So I guess just to be clear, I'll do it both ways. All right, I either sort of move that one group up or swap these 2. Ah, I lost my double bond somehow. There we go. All right. To be clear, though, you would only include one of these because these are identical. Right? I was just showing you the 2 different ways that you can draw that same structure. Bottom line is you need to take your original one. This would be the E stereochemistry right here. To get the Z, you need to pick 2 groups on either side of the double bond and swap them. Cool. And then lastly, you're going to tell me which one of these would be the major product and which one of these would be the minor product. Or minor products, right? We got 3, so 2 of them will be the minor. Well, I say that. That's not necessarily the case. Yeah. All right, so in this case, my major product would be that E stereoisomer. It is more substituted, but it also has its largest groups not on the same side, on opposite sides of that double bond. All right, and then lastly, because I mentioned it, let's throw this last sort of example on here. All right, so let's do this. Okay. I'm going to get at my first two products pretty easily by just making a double bond on one side, making a double bond on the other side. Cool? All right, and then are these my only two products? No, in fact, how many products do I have total? 4, right? Because both of these here have stereoisomers. Both of these are the E conformation, so I need to get the Z conformation. And again, I'm going to do so by swapping two groups, and I can pick either side of that double bond. Again, it tends to be easier to pick the smaller side. Okay, but I could have also, picked this up and flipped it like a pancake, and you would have gotten the other version that you could have drawn. All right, so same thing here. This one also has a stereoisomer. I'm going to do the same thing. Now it's an ethyl group. I got to pick up 2 carbons and move them, but the same principle. Boom. Okay, so we got our first 2 products. These are both the E conformation. We got our second 2 products. These are both the Z conformation. Which one's going to be the minor of the 2, the E or the Z? The Z. So these are both minor products. All right, what about these 2 E products here? Is one of them preferable over the other one? Does one of them have bigger groups on the same side of that double bond? No, they're both elongated as much as they can be. All right. Do they have different degrees of substitution? No. So both of these would be produced in about the exact same amount and considerably more than the other 2 products. So both of these we would call our major products. Cool. All right, so we are going to talk about the mechanism of this dehydration reaction. And as I hope you could tell by our reagents that we used, this is a reaction that takes place under acidic conditions. And we're going to start to hear this kind of a lot, this idea of acidic conditions or basic conditions for our mechanisms. Okay? So, oftentimes in our mechanisms, and what we're going to see here, is there's a lot of proton transfer steps. There's a lot of steps where a hydrogen is transferred from one molecule to another. All right? And importantly, that particular reaction, we got a special name for it. Those are acid-base reactions, right? Transferring of a proton. Something's a proton donor, the acid. The other thing's playing the role of the proton acceptor, the base. All right? So under acidic conditions, when we need our proton donor, our acid, all right? Remember, I mean my H plus donor. We are going to use hydronium. Okay? Now, just because we're under acidic conditions doesn't mean that we only need acids, all right? There are going to be a lot of proton transfer steps that is going to require something to accept a proton as well, to be a base, right? Now, I can't just use our normal go-to default base that we have in our head is hydroxide, right? That's the thing that's been drilled into our head is a base over and over again. But hydroxide does not survive under acidic conditions, right? It's going to react into water immediately. So my base that I'm going to use when I specify acidic conditions, the thing that's going to play the role of the proton acceptor, isn't hydroxide, too strong of a base. It's going to be water. Water can accept a proton. It will then become a hydronium ion. And again, hydronium ions we can have in our acidic conditions. All right, so by acidic conditions, when we're doing our mechanisms under acidic conditions, one thing that we need to make sure of is that we don't have any strong bases. All right, now, truthfully, the devil may be in the details for a particular reaction. Maybe it's not water, but an alcohol, if that's your particular solvent that's accepting protons. There can be some more complications, but this is kind of our default here. When we think acidic conditions, we think kind of an aqueous acid being added. So we got H3O molecules rolling around, hydronium ions rolling around, and water molecules. Okay, so when we do our mechanism here, this is what we're going to use in these proton transfer steps. All right, cool. So we're going to look at this mechanism here for a tertiary alcohol. This is what's called an E1 mechanism. So let's just take our tertiary alcohol here. All right, we're going to put in our hydronium. All right, and I want you all to do, we're going to do something scary here. I want you all to try to see if you can't come up with the mechanism for this dehydration reaction. We're going to lay out a few tips here. So first of all, always incredibly helpful to know where the heck you're going in your mechanism, right? So let's put our product. This is our target here. If we do all our steps correctly, this is where we'll end up, right? We're trying to bridge the gap here. Okay, now the other tip that I'm going to give you here is we've talked about how this hydroxyl group is actually kind of a pain in the butt to get rid of. It is not a good leaving group at all. And so every single reaction of these alcohols has involved this trick of making it into a better leaving group. All right, so I'm going to tell you the first step in our mechanism is one of those tricks that we use to turn it into a better leaving group. And it's the same trick that we used in acidic conditions before, where we're going to protonate that OH group to turn it into that better leaving group water. All right? Cool. That's the only tips I'm going to give you. Now, try to see if you can't get to A to B. Again, we're going to protonate OH to turn into a better leaving group. Okay, one thing that I want to sort of stress here is, as we've discussed, in this reaction, you not only have to lose that OH group, but you have to lose a hydrogen as well. Okay, so somewhere in our mechanism, we got to have a hydrogen taken from that carbon. All right, let's do it here. So the first step is to protonate that alcohol. Okay. Now, because this is a tertiary alcohol, the next part of our mechanism happens in 2 steps instead of just 1 step. And if you did it in 1 step in your sort of scheme here, I would forgive you, and that'd be great just for sort of getting a mechanism correct, which is hard. All right. But because this is a tertiary alcohol, it goes through what's called that E1 mechanism, where it forms a carbocation intermediate. And this is the hard part here. Okay, this is the hard part, is forming that new pi bond and getting rid of that hydrogen. And importantly, that all happens in 1 step here. All right? In order to do this, I have to draw in this hydrogen explicitly, because I'm going to need that bond in my mechanism. All right? So I'm going to draw in one of those hydrogens on that neighboring carbon. You can draw in all 3 if you want, but you definitely need at least 1. Okay? And that's because this is the pair of electrons that's going to come down and reform that carbon-carbon pi bond. All right? To be clear, I guess I spaced this out way too much. This new carbon-carbon pi bond, our whole goal in this reaction, that pair of electrons, is that pair of electrons that used to be between carbon and hydrogen, right? That neighboring hydrogen. All right, but hydrogens don't just go flying off into space here. There has to be something to accept that hydrogen, what we call a base, right? And again, what do we use as our base under acidic conditions? Water. So I'm going to have to draw in a water molecule here to play the role of the base and accept that proton. And that's how we get our dehydration product. Okay, so E1, our tertiary alcohols undergo an E1 mechanism, which means they have that carbocation intermediate. And when we think carbocation intermediate, we're like, oh crap, because what do we got to worry about with carbocation intermediates? Shifts. Okay, but good news, we're talking about tertiary alcohols. So by definition here, we've already formed our nice and stable tertiary carbocations. Okay? So because we're talking about tertiary alcohols to begin with, we actually don't have to worry about any shifts here. Our life is kind of already complicated enough with all those alkene products. All right, then that begs the question, all right, well then what about our primary, and really it's the secondary ones that would mess us up quite a bit. I guess the primary ones could too. So this is where our book tells us that these go through an E2 mechanism. Which is when, instead of being 1 step where the alcohol leaves and then the hydrogen is taken off in a 2nd step, this all happens in 1 shot. So there's no carbocation intermediate that forms. The leaving group leaves and the hydrogen leaves all at the same time. Yeah, we're going to sort of, for the sake of time, leave it at that. leaving group leaves, and hydrogen is removed, and new pi bond forms. All in one step. You would have first talked about these mechanisms in the first semester with regard to alkyl halides, and you can reference the book. I'm not going to put too much into this because, to be quite honest, it's a lie. I'm sure that there is some bit of competing mechanism, but this is a particular reaction that I've done a ton because I just think it's super interesting, and you always get a crap ton of carbocation shifts regardless of what alcohol you start with. You can start off with one octanol and you get every single octene product that you can think of, all right? So there's a lot of crazy crap that happens here. I think it's kind of a lie to be like, oh, it's E2. Maybe there's a little bit of that going on, but there's a lot of E1 going on as well. But the bottom line is this is gonna make our lives way too freaking complicated, all right? We're gonna live in a nice ideal world where we don't worry about hydride shifts and such when we're talking about primary and secondary alcohols. Again, our life with dehydration reactions is already difficult enough without worrying about every shift under the sun, so we're gonna leave it at this, okay? Tertiary alcohols, I would expect us to know that dehydration mechanism for. Cool, all right, enjoy your weekend.